Hi, my name is Walmi Cuello Jimenez. I will be presenting the study on fatigue damage monitoring of a composite step lap joint using distributed optical fiber sensors, a collaborative effort between Monash University in Australia and the Australia Department of Defense. Here we're looking at how the composite content by weight has evolved over the last decades. The two major aerospace companies, Boeing and Airbus, have increased their composite content on airplanes from 5 to over 50% over the last 40 years. Large composite structures are typically manufactured by adhesive joining of separately manufactured parts. This presents several advantages, especially when compared to mechanical joints: reduced labor and costs, uniform load distribution over larger areas, reduction in stress concentrations. However, there is a key disadvantage of this technique, which consists of yet stress concentration at the edge of the overlap. In order to minimize the peak stress, or the stress concentration, many groups have proposed the use of step-lap joints as an efficient joining methodology. A step-lap joint consists of manufacturing the parts with a series of steps that result in greater bonding surface area, reduction in stress concentration at the end of the overlap, high joint strength, and more importantly allows for efficient and effective joint repairs. Ultimately, reaching more than 50% composite content by weight in the aerospace industry could not have been achieved without the use of step-lap joints. Consequently, this work focuses on structural health monitoring and evaluation of step-lap joints by employing distributed optical fibers to monitor fatigue failure. An optical fiber consists of three key components: a core, an annular cladding, and a protective coating. They have multiple advantages, including immunity to electromagnetic interference, resistance to corrosive environments, the ability to multiplex multiple signals into a single fiber and then allow for measuring multiple variables, allowment of embedding the fiber into composite materials for real-time and in-situ monitoring. However, there are two key disadvantages: the need of optoelectronic equipment in order to translate the optical measurements into meaningful physical variables or measurements such as temperature and strain, and the bandwidth required for these devices to be able to post-process all the data collected. There are 5 key sensing mechanisms for structural health monitoring: intensity modulation, polarization, phase, scattering, and spectral modulation. Perhaps will scattering modulation be one of the key measurements. There are multiple applications of optical fibers. Among those we have gas sensors, temperature and strain in situ monitoring by embedding the fiber into the composite structures, and fatigue monitoring. The sensing mechanism used in the present work consists of Rayleigh optical fiber distributed reflectometry coupled with swept wave interferometry, or SWI. The sensor interrogator uses an optical distributed sensor by Luna Technologies with spatial and temporal resolution of 5 and 100 of a second respectively. The SWI system is based on the Mach sender interferometer, which consists of a laser that generates continuous wave, an optical fiber which guides the light through the system, couplers which split the light to and from the arms of the interferometer, reference arms that provide reference or benchmark signal to that of the tested fiber, and finally a detector which detects the incident optical intensity. Now in this work, the interference patterns are generated as frequency is tuned. These patterns are a function of amplitude and phase of the tested fiber. By employing an inverse Fourier transfer of these patterns into the time domain, it is possible to construct a map of this pattern as a function of distance. It is also important to specify that the Rayleigh amplitude is unique to the fiber being employed. Therefore, as you stretch the fiber, the frequency pattern is also stretched. And as the frequency is proportional to temperature and strain, it is possible to calibrate optical change or a frequency change and a wavelength change into a resultant temperature or strain measurement as the equation below is showing. This equation, lambda is the wavelength, b is the frequency, k sub t and k sub epsilon are the temperature calibration and strain calibration constants. Finally, the fiber uses an acrylate coated 250 microns with no protective jacket in order to eliminate any slippage error introduction into the system. The specimen uses a 24-ply thick high-splay carbon fiber prepreg with the sequence shown of 090, 45 minus 45, 45 minus 45, and 090, which is repeated 6 times in order to generate the 24 fly. The schematic on the right shows the dimensions of the specimens tested. The adhesive used was a FM302K by Cytec in Australia. Each step of the lap joints has a thickness of 0.90A, and the bond line area, as per the schematic, is 90 times by 25.4 square millimeters. The fibers were bonded onto the top surface of the specimens following the red dotted line pattern with Loctite 406 component. And finally, the specimens is placed into a loading cell with a capacity of 100 kilonewtons to perform the fatigue testing. As you can infer from the setup, the photo of the fiber was split into fiber 1 on the left and fiber 2 on the right for experimental purposes mainly. Now the fatigue testing is designed to increase by 1000 microstrain every 100 cycles with a minimum to maximum stress ratio of 0.1 throughout the entire experimental evaluation. The first experimental evaluation consisted of determining the ability of the system to monitor dynamic strain. Now for this, the midpoint of fiber 1 was evaluated by exposing the specimen to a fatigue loading of 5 Hz while sampling at 17 Hz. Results show only the first 4 seconds of data, where it indicates that the strain ranged from 200 all the way to 2000 microstrains. And by employing an FFT, a cyclic frequency of 5.11 Hz and a maximum microstrain amplitude of around 870 microns were determined. Interestingly enough, results indicate that the strain measured by the distributed optical fiber system corresponds to the fatigue loading profile. Second evaluation consists of monitoring the ability of the system to measure distributed strain across the entire fiber prior to fully diving into the fatigue evaluation. Results show the effect of different loading regimes on distributed strain. 4 key features can be immediately identified. 1. Fiber 1 and 2. Results are essentially mirrors image of each other, which makes sense since they are both in the axial direction with respect to the load being applied, using the opposite sides. Second, the consistency across both fibers proves that optimum bonding between the structure and the fiber has been achieved. Third, the top region shows greater deformation than the bottom one, which is attributed to the geometry of the specimen, with the top region having a shorter bonded thickness. And fourth, lastly, reduced strain is observed in the loop area, which is expected considering that the fiber is intended for measuring strain, mainly in the axial direction. Once it is proven that the system can measure distributed strain along the fiber, the focus turns into monitoring fatigue and ultimately the path to failure point of the system. The strain was monitored again at midpoint of fiber 1. The entire fatigue test was conducted for about 14 hours. Now in the strain versus cycles chart, it can be observed that the loading increased by about 1000 microstrain after the first 200,000 cycles, at which point the load cell was set up to stop by 1 minute prior to increasing the loading scheme by 1000 microstrains and maintaining the stress ratio of 0.1 throughout the entire experimental evaluation. All of which, as you can see from the results, was detected by the distributed optical fiber sensor. Now zooming into the last 35,000 cycles, results reveal that the failure occurs after about 254,000 cycles. The strain gradually changes over the last 3,500 cycles prior to failure. Perhaps more importantly, the ability of the distributed optical fiber system to measure strain change before failure takes place and the location of the fracture point can be used as an indication of damage along the structure. Then the ability of the system to generate a 3D distributed strain map is evaluated by monitoring the strain of fiber 1 over multiple cycle loads. Results depicted in the 3D chart of strain versus cycle versus length during the 3000 microstrain loading regime clearly reveal the point at which the structure fails, that the strain changes significantly over the last 4000 cycles, and also more importantly probably that the distributed optical fiber sensor's capacity to perform real-time and continuous monitoring of structural health in regards to both temporal and distributed changes to the structure. Now the photos of the specimen after failure indicate that first, ply failure takes place, followed by net tension and adhesive failure. Lastly, to complement the work, it was necessary to further prove the ability of the system to measure the life cycle of the specimen. This was accomplished by focusing on the last 50,000 cycles using 200,000 strain measurements as the 200,000 cycles strain measurements as a reference. Results from strain measurements across fiber 1 from 0 to 90 millimeters, the bonded area, indicate that the strain at the bottom edge is relatively constant for 220 to 250,000 cycles. On the top, there is a gradual increase in strain over the same cycle range. However, this was due mainly to the change in adherent thickness from the top to bottom, with the top being only 4 plies thick, whereas the bottom was 22 plies thick. Now, the disbond or progressive bond failure can be attributed to the increase in strain with the increased number of cycles. Eventually, in the last 4,000 cycles, the loading scheme of the loading screen, cracks are attained from both sides, top and bottom, of the bonding interference, as seen during the cycle ranges from 252 to 254,000 cycles. All combined prove that the distributed optical fiber sensors could be ideal for damage assessment of monitoring and fatigue crack growth along the bond lines. Conclusions: the distributed optical fiber sensing is an attractive methodology for structural monitoring of composite material. Distributed strain evaluation proved able to identify fatigue damage and eventual failure of a step lap joint. Distributed strain measurements allow for in situ real-time monitoring of the condition of the bonded step lap joint prior to a catastrophic failure taking place, and of course without the need of any inspection. Finally, these methodologies allow for both in-flight and on-the-ground detection and monitoring of composite structure from both temporal and spatial references. Thank you.